We're going to end with our story number 3, which is our story about, or related to at least, unidentified anomalous phenomenon, which is more commonly known as UFOs. And before we kind of get into the 2 papers themselves, I kind of wanted to set the table a little bit because this is a subject and an issue that is extremely popular, not only in the US but globally, and has in recent years gotten a boost because of a variety of events that have been happening, particularly within the apparatus of the US government, intelligence, and military industrial complex structures.
Yeah.
And, this is a subject I've talked to you about a lot.
Yeah, and you're very passionate about it.
It's something that I've interest in. I work at a nonprofit that's working in this space, the Disclosure Foundation. And one of the things that people always get caught up on is origin. And what I would ask is that we sort of keep origin to the side for a second in this conversation, and just talk about what is without trying to ascribe an origin to it, because these are all things that are happening regardless of what you want to ascribe the origin to. And it's interesting regardless of what the origin is. And so I'm going to do a quick retrospective on kind of the recent history of the UAP subject. That is the context in which these 2 papers are coming out. And so for many people, they're probably familiar with the 2017 New York Times article that came out that basically talked about the fact that there's these US government programs that are studying UFOs that have existed for some time. And that was sort of the catalyst for the modern era. The subject has a long history prior to that that is outside of the scope of this episode.
Yeah.
And so we're not going to touch on sort of the what I call the legacy era of the subject. But after that New York Times article came out in 2017, it contained 3 videos. This was the first time we were getting videos with chain of custody from the US government that were showing these anomalous objects, right?
Okay.
But it was still only put out by the New York Times, which people will have differing opinions about the quality of that institution as a newspaper. That's changed since that time period. But the Pentagon actually confirmed that what are colloquially known as the gimbal, FLIR, and go fast videos are legitimate videos that have chain of custody to the US government. That happened between 2017 and 2019. What sort of proceeded from there was an escalation of the issue from a national security perspective. So in 2020, the then Senate Intel Minority Leader, Marco Rubio, who is now the National Security Advisor in the Trump administration, was one of several senators who called for there to be an unclassified report to be created by the Department of Defense around what are these UAP? What is this unidentified anomalous phenomena? In 2021, the Office of the Director of National Intelligence delivered that report in which they stated that there were 143 unexplained cases that, again, this was largely driven by Navy and other pilots basically saying, look, this is a safety of flight issue and we need to be able to report and address this just for our day-to-day operations.
Right.
Again, independent of origin or any of these other issues. The DoD then created, this UAP task force, which was this sort of temporary task force that went out to both the intelligence agencies and the military sort of apparatus to try to understand, are you all seeing this? Where are you seeing this stuff? What is going on here?
Yeah.
That eventually now rolled into what we now know as this permanent Pentagon office that's called the All-Domain Anomaly Resolution Office. That was established in 2022. And that office was congressionally mandated to be created after that initial report came out. Because Congress is basically alleging that the executive branch, which runs the intelligence agencies and the military, are not providing them the information about what's happening as it relates to this subject specifically. And it's important to note that the term UAP is a specific term of art that does not include any other form of unmanned aerial systems. So this is drones, this is, undersea, unmanned, like those are all discrete and defined.
Yeah.
And there's processes we have to deal with that. The reason why this became an issue within the government is that these platforms were exhibiting flight characteristics or behaviors that were beyond the scope of what was deemed as current or even next generation technologies. This has then been followed up by multiple hearings within the House and the Senate on this issue, and it's culminated with legislation that part of which was passed, that was proposed initially in 2023, but then passed in 2024, that mandated that executive agencies release information around the history of this subject. I mean, there's literally a colloquy between Senator Schumer, who was the then Senate Majority Leader for the Democrats, and Senator Mike Rounds, who was a Republican, where they were sort of going back and forth, identifying that, that this is something that has been an ongoing issue that Congress has been going after and the executive branch has been unwilling to provide information on. So this is sort of a live issue. NASA had a UAP independent study group. They put out their own report around this issue. They are obviously struggling for funding, so it's not something that they're spending money on because they're trying to just survive as it is.
Yeah.
There's been multiple whistleblower protections that have been passed. There's been defunding of UAP programs for the intelligence community. I mean, there's this long list of indirect evidence around this subject, but there's been a dearth of scientific research.
Yes.
Really, the main primary thing that has existed in this space, particularly in the last couple of years, have been research papers that have been trying to define how to study this subject because of the reproducibility problem and the stigma, both of which are big issues. And the reference point that has been addressed is like multi-messenger astronomy studies has been the reference point for how to try to deal with this problem. But there are two papers that have just come out that are a first of its kind in terms of having actual data that, again, can be potentially either reproduced or replicated in other arenas from the Palomar Sky Survey. And we're going to kind of go in from a first principles perspective to understand what these papers actually were talking about.
Yeah. Yeah. So there's a lead author, Dr. Beatrice Villarroel.
Villarroel, yes.
I hope I'm saying that right.
Yes.
So the lead author, Dr. Beatrice Villarroel, she actually covered this issue before in her 2021 paper.
Yes.
That was published in Nature Scientific Reports. It was on 9 simultaneous transients occurred in April 1950.
And it's important to note that like research on this has been done.
And this is kind of a follow-up paper, but it's, I believe, a lot more thorough. And I just thought that the way that the research was conducted, the science sort of speaks for itself, and then the interpretations come afterwards.
Sure.
But on this podcast, we always focus on from first principles. What is the science that you did, and does it warrant the conclusions that you put out?
Yes.
Right. So we're going to start with these papers. The papers focus on the Palomar Observatory Sky Survey. Okay. This is POSS-1. It was a sky survey that was taken up by the Samuel Oschin telescope, which is a camera that is mounted on the Samuel Oschin telescope at Palomar Observatory. There you can see the telescope itself. It's got a Schmidt camera, and this thing is specialized for wide field photography. These cameras are actually pretty insane because, so that camera, the camera that is attached to it, has a field of view of 6.6 degrees by 6.6 degrees. Okay, so 6.6 degrees by 6.6 degrees. The full moon, for comparison, is half a degree. It's about like if you were to put your thumb right in front of your face, the size of your thumb is about half a degree. This is 13 full moons by 13 full moons. So it's 170 full moons big is the field of view of this camera, right?
Okay.
And because it's so big, there's a specialized camera called a Schmidt camera, and what it does is you've got a primary mirror, right? The mirror is about 1.2 meters. That mirror then goes into the camera. You can imagine the light is getting warped, right? As the light comes in, it gets warped, and so the edges of your field of view are going to get distorted.
Yep.
This specific camera is specialized for that kind of wide field photography. So it corrects for that distortion. And even then, the focal plane is actually not flat. You know how in like a camera, your CCD is basically a flat piece of equipment because all of your light is coming onto a flat piece of equipment. Here, because it's such a large field of view and it's so big, the focal plane is actually curved. So in order to get a photograph, your photograph, the plate in this case, the photographic plate, and these are all photographic plates that are used, also has to be curved. And so you got to like warp it before you slide it in there and get this photograph. I thought that was really cool.
That's interesting.
Like the amount of stuff that needed to happen in the 1950s in order to get these kinds of large field of view photographs, right?
Given the technology we had at the time.
This is purely photographic, which means that the other cool thing is that the telescope that we just saw, that telescope is an equatorial mount. Okay, and what that means is that one of the axes is parallel to the Earth's axis of rotation, and so all you have to do is rotate along that axis, and it'll follow the stars as the Earth rotates underneath. Right, the stars are all gonna move in a circle around the North Star. And so in order to track a single spot in the sky, the telescope has to rotate with the Earth so that it points in one direction in the celestial sphere. And in order to actually do that back then, they had a manual astronomer that would look through a 10-inch smaller telescope to a guide star and then control the telescope manually to keep that guide star in the exact same position. So there was a lot of like manual stuff going on back in the day. And I think this is really important to see, to understand how the data was collected, right? It's not with this modern technology where now everything is automated and nothing is actually in equatorial because it's easier to make bulkier telescopes in the azimuthal mount where I can control both axes with a computer, and I just have to like do the calculation and control both axes, and I'm fine. So this guy's survey produced 1,000 photographic plates, about 1,000, but one in red, one in blue. So then you'd have about 2,000. This is an example of one of the photographic plates. It's a 1 degree by 1 degree patch of the plate that is targeting Pleiades, the Seven Sisters. And the haziness that you see, that's actually not a defect. Those are actual clouds around those stars, those dust clouds around those stars that are creating that. It's a beautiful, beautiful example of one of the photographic plates that was actually taken during that time. The typical exposure was about 45 to 50 minutes. What we're focusing on here are the red sensitive plates. They used to take red sensitive and blue sensitive. Here we're focusing on the red sensitive because that's what was used in the study here. Okay. And the limiting magnitude is 22 in terms of apparent brightness. The higher the magnitude, the dimmer the thingy is. And this is about 1 million times fainter than what the human eye can see. Okay. So that's what's limiting the faintest object that this telescope can see. Okay.
That's like the lower bound.
Yes, that is the lower bound. So that's the telescope that we're using. And that's how we're getting these images. Now, the photographic plates. We got to talk about the photographic plates.
We got to talk about the plates.
What does that mean?
Yes.
So photographic plates are 14 by 14 inches. And these 14 by 14 inches are placed at the back of the camera where all of the light is coming in. It's 1 millimeter thick. These are incredibly thin for how big they are. They're like the size of a record, a vinyl record. They've got they've got a photographic emulsion on them, okay? A light-sensitive silver halide crystal layer. Usually it's silver bromide, and that's suspended in gelatin, okay? Bromium is the halogen that they're using here. Halogen is like that column on the periodic table that's second to last on the right. these plates are bent, as I was saying, so that they can match the focal plane, which I thought was just really cool to think about.
Yeah.
And then the process is a photon comes in from your telescope and it liberates an electron in this silver bromide. And that electron, that liberation of the electron forms a latent image speck. You've got this free silver atom, okay, that creates a silver atom cluster. Then during development, that latent image speck catalyzes, and the silver bromide that's around there goes and turns into black metallic silver. Okay? And then finally you have a washer, a kind of fixer that removes any unexposed silver bromide. This is like the old school, where you like wash the thingy.
Yes.
And then that removes any silver bromide. And what you're left with is a permanent negative image. And that's why in the previous image that you saw, if you actually go back to photo 2, you'll see in the previous image, the dark spots are actually where the light is. Okay?
Right.
Because that's where the silver is getting deposited.
Yes.
Okay?
Yes.
So you get this negative image
Right.
of the dark is actually where the light is coming in.
Got it.
Okay? And the white is where there was no photoreaction that happened. Okay? And so that's how we actually get these photographic plates.
That's what a photographic
That's
plate
what a photographic plate is. And that is what the chemical reaction of what a photographic plate means. Okay? Now, what this sky survey is doing, and the data that this particular group used is the digitized version of those photographic plates. Okay? So the digitized version in the 1980s and 1990s, we did a digitization process where those glass plates used micro densitometers that basically went through and digitized these photographic plates. You've got a light beam that measures the opacity of the photographic plate, and that converts that opacity into a digital pixel value. So the more opaque it is, that means that there was more dark, right? There was more darkness.
Right.
And then if there's more darkness, that means that there's more light over there.
Yes.
And so now you've converted from photographic plates to a digital sort of pixel values.
Yes.
Right?
Yes.
And there were two digitization processes that happened. Okay. There was the digital sky survey that was done with a pixel size of 25 microns.
Okay.
And then there was a super cosmos sky survey.
Yep.
And that was done at the Royal Observatory of Edinburgh with a higher resolution of 0.7 arc seconds per pixel.
Got it.
Okay. So the first one was 1.7 arc seconds per pixel. And then this one's 0.7 arc seconds. So it's just like more grainier detail.
Yeah.
Sort of think about.
It's a slightly higher fidelity.
Yes, exactly. And now you've got a vetting step, right? Where now we can create computer algorithms that look at these digital photographic versions and then try to find transients, little spots in the sky that aren't there in current photographs of that patch of the sky.
But that were there.
That were there back then.
Okay.
Right? And what we can also do is we can rule out any scanning artifacts because we've got two different digital versions of the photographic plate. So if something happened in the scanning where I got a little speck, that shouldn't be there in both at the same spot.
Yeah,
right. The probability of that is insane.
It's insanely high. The point is the digital scans, there's two versions. And so if someone was asleep at the wheel when they scanned version 1, it should not be there in version 2 at the exact same spot in such a precise way. And so what you're sort of, there's a layer of validation.
Yeah, there's like a redundancy
here because we have two digital.
Yeah, we have two digital versions of this.
Okay.
And so now we get into the Vasco project, right? Which is the vanishing and appearing sources during a century of observations. This is led by Beatrice Villarroel. And the point of this project is to have a systematic comparison between the digitized versions and modern sky surveys, right? You look at what the Palomar Observatory saw back then,
Yes.
and you look at what we're looking at right now.
Yes.
And you've got an automated software that flags these vanishing, the present then, missing now, right? And there's also appearing. So not present then, but appearing now, right? You've got an automated software that flags these things. And initially you've got a catalog of 100,000 transient candidates. And here we're seeing two different images, one from POS 1, which is the first sky survey, and POS 2, and the circles represent two little spots that you can see are exactly not there in the second one, right? It's like pretty obvious that those two dots were there before and now they're not there now, right? And so that's a transient. You've got a point-like source that's there in some plates, but in the later plates it's not there.
And the idea is, we have 2 points in time, and we should be seeing identical things in both those points in time.
Yes. And if it's a star, then yeah.
It's not identical.
It's not identical, right? So people are going to be skeptical about this, right? For example, it could just be plate defects.
Sure.
Right? Both this point of source of light or whatever, this thing that we're seeing in the photographic plate, it's there in both the digital versions. Well, that means it could just be in the plate, right, itself. What is a hallmark of something that is in the plate? And this is something that comes from Nigel Hambley at the University of Edinburgh. He's one of the critics. He looks at something called the full width at half maximum of these points of light, okay? So the full width at half max is basically, imagine you've got a Gaussian.
Yep.
What you're looking for is what is the width of that Gaussian when the height is half the peak height, okay? And what this tells you is something about the noise in the data gathering process. Now, I told you this telescope, right? It's traversing the night sky.
Yes.
And it's being controlled by a human being. Well, there's going to be a little bit of noise in how I control that telescope as it tracks, right? So even a stationary point of light is going to have a little bit of jitter, right? As I move this telescope, the telescope is going to not totally track it completely. And even a point of light like a star that is definitely stationary,
yes,
over the 50 minutes at least,
yes,
it might be moving over like several years, but like over 50 minutes, it's stationary. That's going to have a little spread in my photographic plate. And what he noticed was these transients, the ones that sort of appear and disappear, they've got a spread that's way smaller than the stars. Mm-hmm. Okay?
Mm-hmm. Yeah.
And that, to him, was a telltale sign that this is a defect. Because if it was a light source, then the light source should have the same sort of error that the stars do.
Because they're all light.
Right? Does that make sense?
It does.
Right? Like all of the other things have the same sort of spread because it's from the same jitter of the telescope.
It's uniform across the system.
Right?
Yeah.
It's a key thing.
Yeah.
Now, the contention is, the sort of counter argument is, well, if it's truly transient, meaning like it only like lit up for a minute or a fraction of a second and it had a bright signature, then only one part of that 50-minute exposure is going to have that light come on, and then it's going to go away. So then, of course, the full width at half max is going to be way shorter because it's not going to have time to accumulate that noise.
Yes.
Right? But now we're at a degeneracy problem, right? Because a genuinely short-lived astronomical event, right, something that happens for a fraction of a second, is going to look identical to a plate artifact.
Got it. Right.
Right,
yeah. So
it's like you're looking for a short-lived astronomical event, but that's going to look exact,
Yeah. How do you distinguish between what is being argued as a plate artifact versus a true short-lived transient event? Because it's hard to distinguish between those two.
Yeah. The measure that we're using is degenerate to discerning between one or the other. Does that make sense?
It's one of the two.
Yeah. But like the measure that we have, which is this full width at half max, is like it's going to be the same for both.
Got it.
Right?
Yes.
So which one is it?
Yes.
And that's why there was a necessity for an independent line of evidence.
Okay.
And this is where we're getting into the two papers that we have now.
Okay.
So it's this challenge of, well, it could be a defect or it could be a truly transient object. Which one is it?
And the interesting note here, just as a caveat or a point of order, is there was a emphasis on this being, the Palomar Sky Survey, which happened in the 50s, was pre-Sputnik
Yes.
Sky Survey. And nowadays, when we talk about transient light artifacts, it's Starlink, it's other satellites, other whatever, Chinese classified platforms, but there's a lot of stuff that we have now put up there. And so it is much easier nowadays to say, oh, it's X, Y, or Z.
Yep.
One of the interesting aspects of why this distinguishing between whether it's a plate artifact or not is if it's not, we're seeing these transient light anomalies at a time period where we
at least didn't put anything up there, right? On purpose. Right? This is from November 1949 to December 1958. This is before Sputnik.
Which could be interesting.
Yes.
Because of the fact that it can't just be pointed to being Starlink passing by.
Exactly. And so now that is where we're getting into the two papers that have come out from the Vasco project, okay? What they've done is with the first paper, they're doing a spatial arrangement on individual plates, and they're arguing about the transients, how they look on individual plates, and where they are in the night sky in terms of when these photographic plates were taken, where was the Earth's shadow, and if we can do some kind of statistical comparison and really show that these are stuff that's in the night sky and not photographic plate defects. And then there's a second paper that talks about temporal correlations in time between the stuff that we see in the photographic plates and stuff like nuclear tests and UAP sightings, which we'll get to. So, study one. This is the alignment hypothesis. Okay. This is Villarroel and others in 2025 in PASP.
Yes.
The paper is Aligned Multiple Transient Events in the First Palomar Sky Survey. The hypothesis is that these multiple point-like transients are aligned along a straight line on the same plate, which is very unlikely by chance, and they could be real physical objects. And that is the argument that they're making. Mm-hmm. Okay? So they've got a catalog of about 300,000 short duration transients from this Palomar survey that we just went into.
Yes.
Okay? And the first thing that they do is they ask, how many of these things are aligned? They're in a line, okay? And here we've got a photo of plate 5. This is candidate 5. Mm-hmm. There's 5 different thingies that are all in a line, okay? And they use this thing, a statistical framework from Edmonds and George, published in 1985, and it calculates how often you would expect these things to happen by chance. Okay? And they find a sigma of 3.9 that this is not chance. Okay? 3.9 it's pretty high. Okay? It's not like 5 sigma.
Which we've talked about in our previous episode about the strongest evidence yet for life on an exoplanet, which was 3 sigma.
Which was 3 sigma. There's 3.9. It's higher, but it's still not 5 sigma.
Sure.
Right? But it's kind of interesting. Okay? And this is just candidate 5. There's other candidates that also have around 3 sigma. Right? Okay. And they go through this in their paper. That's actually not personally what I found the most interesting. The alignment is like, no, I don't know, by chance. I don't really know how to reason about that in my head, about how often to do things by chance. And also the framework, the statistical framework by Edmonds and George, it relies on a bunch of different things like the number of objects in the sky, the assumption about the density of objects, how high they are, like all this other kind of stuff, right? The Earth's shadow test is, I think, a decisive diagnostic. So here's the logic. You've got the sun, you've got the Earth, and the Earth casts a shadow on the rest of space, right? When the moon goes in the Earth's shadow, that's how you get a lunar eclipse. So, if we were to think that all of these things are plate defects. All of these transients are plate defects and not actual objects in the sky that are reflecting sunlight, then if they are plate defects, the number of things that are happening in Earth's shadow should be the same as outside Earth's shadow.
Right.
Because it's not dependent on whether the thingy,
right.
whether the patch of sky I'm looking at is in Earth's shadow or not.
Right.
If, on the other hand, these objects are reflecting the light from the sun, then there should be fewer transients when I'm looking in Earth's shadow
Right.
than when I'm not.
Right.
Okay? And I know the coordinate of the spot in the sky where I'm looking, right? Because each of these photographic plates has a right ascension and declination, which is our latitude and longitude in the sky. We have our time of day. So from that, I can calculate which patch of the photographic plate is in Earth's shadow and which patch is not. I do have to do an assumption based on like how high I think these objects are, but they make an argument which I actually don't quite fully understand, but they make an argument that these objects are probably at geosynchronous orbit, which is 42,000 kilometers. And at that altitude, I can calculate which objects or which part of my photographic plate is going to be in its Earth shadow and which part is not. Right? And then from that, I get an expected number of 1,200 objects, but I only observed 349.
Mm-hmm.
So that's a pretty statistically significant sample. And this is where I remember when you first came to me with this story, you said 22 sigma significance, right? The statistical significance. I was like, what are you talking about? This is what they're talking about.
Right.
They're talking about that like the 349 is so far away from 1223. It's 22 sigma away. They actually did a more realistic comparison where what they did was they looked at the actual sky because this was actually kind of cool. So the photographic plates in Palomar didn't uniformly sample the entire night sky.
Right.
The 22 sigma comes from the assumption that the photographic plates are completely uniformly sampling the night sky. On the other hand, some patches were looked at more than others, right? And some patches were completely missed. So what they did was they did a more realistic simulation where they said, okay, suppose I only looked at those patches and I randomly generated objects. How often would I see defects versus not defects and all that other kind of stuff? And there they get a lower significance, but it's still a lot, 7.6 sigma. That sits better with me. Okay?
Yeah.
7.6 seems more reasonable. And the benchmarking that they did kind of made more sense to me, right? Because they're taking into account this prior distribution of like where the telescope was looking rather than an assumption that, oh, it just looked everywhere. Well, it didn't. Right?
It's not the Vera Rubin Observatory.
Right. It's not just like, this is the 50s.
Yeah.
Right? Like, it took us 80 years to get to the Vera Rubin. So that's the first story. The second story, which is study number 2, this is published in Nature Scientific Reports, and this is correlations with the atomic age. Okay. Transients in the Palomar Observatory Sky Survey may be associated with nuclear testing and reports of unidentified anomalous phenomenon. It's got UAP in the title.
It's got UAP in the title,
bro.
In a Nature subjournal.
In a Nature subjournal, Springer publication,
which is a significant thing in and of itself, given the aversion to doing anything related to this subject from most peer-reviewed journals.
Yeah, I mean, I was pretty surprised myself.
Yeah, when you were like, because I brought it up, you're like, well, what journal was it? I was like, oh, and you're like, wait, really?
Wait, Nature, oh, fine. I guess if it's Springer, we can do it.
We'll cover it if it's Springer.
We'll cover it. Yeah. So here what they're doing is they're doing a more of a time-sensitive approach, okay? Mm-hmm. They're looking at the rate of the transients.
Yep.
That appear in those photographic plates that I talked about.
Yes.
And they're trying to correlate it with dates of above ground nuclear weapons tests.
Yes.
And daily counts of UAP reports. Okay. So the timeline is, again, 1949 to 1957. They get a bunch of transient count. So for every single day, they've got photographic plates and they count how many transients were found on each day. Each day also gets a binary flag on whether it's within a day of a nuclear test
or not.
right? And back then, I think only 3 countries were doing nuclear tests: the Soviets, the U.S., and Great Britain. And then there's also daily UAP reports from the UFO CAT database. And these 3 things are what they're trying to relate.
Yeah, yep.
They use something called a generalized linear model. I'm very familiar with something called a generalized linear model because my PhD had a lot of that. Basically, these kinds of models are what you want to do when things are not just simply linearly correlated to one another. In my PhD specifically, I was trying to correlate the spiking of neurons in terms of many different behavioral motifs, like which way he's looking, how fast he's running, where he is. All of these things can have varied responses that are not necessarily like, oh, if I'm looking this way, I just have more. Maybe it's like a weird response, right? Where only if he's looking this way, there's going to be more. So all of these like different multimodal effects can be captured by a generalized linear model. And that's what they did. It can also simulate weird distributions that aren't like just like uniformly distributed or Gaussian distributed. If you've got like a binomial distribution, which is like coin flips.
Yep.
If you've got, did I see something or did I not? Things like that. It's very good at modeling those kinds of things, right? So there was a correlation to nuclear testing. So the transients occurrence in these photographic plates was 45% more likely within a 3-day nuclear test window. Okay. And the main thing was it was 68% higher likelihood on a day after the test. Right?
Mm-hmm.
It's pretty significant.
It's pretty significant.
There's also a correlation plot that they do with UAP reports where using that generalized linear model analysis, 8.5% increase in transients for every additional independent UAP report on the same day. I don't really care for that as much. Like UAP reports to me are like, I don't know, humans are fooled very easily, and UAP reports are just humans being like, I saw something that was crazy. I can't think of whether there are tests that I could do to see if this would work. Like, for example, what if you like assumed that like on average half of the UAP reports were nonsense? If you took out half, would the correlation still be there? If you did a bunch of samples where you took out half and you looked for correlation, would there be some samples where the correlation would be like way higher? You know?
Yeah.
Like that's something that we used to do in my neuroscience lab and PhD is like, how sure are we that this variable is correlated to this variable? Where if I were to just take out a subset of the data, if the correlation still persists,
then
it's a more robust finding, right?
Yep.
And given the shape of that plot, I'm not sure if I believe it. But the nuclear testing thing is just like that's just there, right?
Yeah.
So So those are the 2 reports. There's one report in PASP that's physical evidence. You've got the Earth's shadow test that a substantial fraction of the transients are sunlit objects, right? And then you've got the scientific reports that's circumstantial behavioral evidence that says that the timing of these transients is affected by nuclear tests, right? There are people who obviously are skeptics, right?
As we also saw with the same paper I just brought up earlier about the strongest evidence yet.
Yeah.
That came immediately with follow-ups from multiple institutions that pointed to why their modeling was not sufficiently robust.
Yeah. Like as of now, I haven't seen any follow-up scientific papers.
Right.
Because all of this data is publicly available. And I actually saw on the 2 papers, it's readily available for people to look at. So I encourage anyone to do their own analysis, actually.
I want to make a funny note. On the paper that I keep bringing up, within 2 weeks, because was it?
It was a week, dude.
It was a week.
Yeah.
Within a week, because it was out of Cambridge or Oxford, one of the two.
Yeah. Cambridge had the original paper, and then the guy at Oxford was like, nah.
And within a week, Oxford came out with the rebuttal.
Yeah.
And then multiple came out. It's been more than a week.
Yeah.
This paper is getting quite a bit of just, obviously, a lot of the science media has is doing a variety of different coverage, but there's not yet necessarily been false as quickly.
Yeah.
There's a number of reasons that could be true.
Yeah. I mean, one of them, I think the big one is probably it's not an active scientific field like exoplanets and exoplanet research is. Everyone's trying to make a name for themselves, right? They've got a career to look after. And so this one is not like something that, okay, so you proved this wrong. It's not going to like give you a leg up in an astrophysical career.
There's no incentive for people who are looking to climb a ladder to do a follow up on it.
Yeah. So that could be one of the reasons. But in any case, the Scientific American actually had an article about it that I was reading, and they showed some rebuttals, right? So there's the Hambly argument, which is from the University of Edinburgh. He's an expert, Nigel Hambly. He's an expert in photographic plate analysis. And his main contention was that full width at half max, right? The fact that these transients are so pinpointy and precise compared to the stars that are kind of spread out because of all the noise from the detectors. And there's skepticism that, this is a classic signature of an emulsion or a flaw or a plate defect. And it's not a celestial object because a celestial object would have this kind of noise.
Yep.
And one of the crucial things that he says is the ultimate arbiter is actually just the physical evidence. The plates are still around. We can take those original glass plates and examine them under a microscope and not examine the digital scans. And under a microscope, it's going to be very obvious whether this is a defect of the silver just like being kind of weird at that point, or if it's a genuine astrophysical source. So I think that's he's proposing a way to
make it go away.
To make it go away. I think that's good.
So if you're interested in doing a microscopic study of the digital plates and you would like to collaborate, just in the comments below.
Yeah, let us know.
Let us know. But and we already talked just previously about, even in the paper itself, a means by which that is not necessarily the likely outcome. However, you can remove it from the
Earth
table.
shadow thing.
Yes, the Earth shadow point. You can still remove it entirely from being the cudgel that you're seeing being put out. Because a lot of times in the coverage of it, people say, oh, it's probably plate defects, without actually explaining how the paper points to why it's not plate defects.
Yeah.
Which is kind of the issue.
The Earth shadow thing is like pretty substantive, I think.
And so, however, it can the beauty of us still having the original plates is that it's falsifiable.
Yes, exactly. There's another one that's proposed by Sean Kirkpatrick, who's
Dr. Sean Kirkpatrick,
former Pentagon AARO head.
We like to call it Arrow.
Arrow. Okay, Arrowhead. I guess that's like a anomaly office or something.
That's the all domain anomaly resolution office.
Oh, okay, got it.
That was created in 2022 as a result of Congress pushing on the executive branch to like give them more information about, again, because military and intelligence officers were coming to Congress saying this is happening and we need help in dealing with this, and we're not getting the support we need.
I see. Okay.
That was the impetus for why the office was established. And its mandate was twofold, which was unfortunate because it was basically a mandate that had conflating outcomes. One was, we want you, Arrow, to take data from the Department of Defense, all of the combatant commands, and the intelligence community, intake it, and then analyze what we're seeing as these UAP reports. And if it's conventional, send it to the office that exists to deal with it. And if it's unconventional, figure out what we need to do to figure out what it is. Right?
Okay.
That was one of its mandates.
Yeah.
The other mandate was a public communications mandate to help to demystify this issue to the public by creating public education materials and this, and the third. The problem with that is you're asking, the Department of Defense, which is not a public communications office, to do public communications. There's a reason why NASA is its own agency.
Yeah.
And you don't have NASA running out of the DoD because we would never get anything out of that structure. So there's sort of a conflate. There's a friction between the two things Congress asked it to do, which is why a lot of the public is frustrated because they are not very forthcoming with. They have thousands of these reports. We've basically seen none of it.
Yeah. Okay. Well, he put his Sean Kirkpatrick. He gave his 2 cents, which I thought was actually quite good. Which was he said, there's nuclear detonation, and clearly this thing is correlated with nuclear detonation. Now, when you have these high altitude nuclear detonations, you can have radiation, particulate stuff that goes away, and it can create transient luminous events like Cherenkov radiation, or even reflective metallic junk like the stuff that made the nuclear, there's going to be stuff that gets thrown out, and that junk could reflect light in the way that we're seeing in these Palomar sky surveys.
This is interesting because I was just at the Seoul conference in Lake Maggiore, Italy this past week, where Dr. Beatrice Villarreal presented these 2 papers. And there was a Q&A section where one of the people actually asked about the Cherenkov radiation as a solution to the problem set. Someone can clip this and put the response. I don't think it's public yet. I didn't write it down, but she did have a response to that issue.
Yeah.
Which I unfortunately can't replicate in this context. But that was brought up by someone in the audience as the obvious next step in the progression.
Yeah.
As an answer to it.
Yeah, I can imagine for Cherenkov radiation, it would probably be streaky rather than single point sources. But if you have metallic junk,
then it's that.
Then that could as it's turning, create that reflective. So to me, the metallic junk is a better explanation than Cherenkov radiation or ionization, because those have very characteristic
Streaks.
Signatures on photographic plates. But one of the challenges that Sean Kirkpatrick said was, we've got GPS satellites now. Why don't we try to reproduce these results with the GPS satellites? I think it's harder said than done, because GPS, there's so many satellites now, right? It's not just you're going to have so many streaks.
Yeah.
So for a 50-minute exposure, you're just going to get completely wrecked by Starlink.
Right.
There's another proposition by Elliot Gillum at the SETI Institute, Search for Extraterrestrial Intelligence. He said, meteors traveling directly towards the telescope could appear as stationary dots, not streaks. It's viable, but now it's traveling directly at the telescope. Okay.
That volume level and simultaneous.
Yeah. It's simultaneous, multiple, aligned.
It's a little challenging.
Yeah, it's a little challenging given the numbers. There's a Princeton astrophysicist, Robert Lupton, who has this look elsewhere effect. He's basically saying that, in a massive data set with thousands of plates, millions of images, finding a few apparent alignments by chance is not that surprising. And you can't actually use the Edmonds and George formula to do that kind of statistical significance to figure out whether stuff is in a line, because there's so many things that are in a line. You can easily fool yourself into thinking that the thing that is in a line is there for some reason, right? And the probabilities need to be corrected for the vast number of stuff that's out there.
This goes back to your not looking at the alignment as the interesting part.
Yeah. And I think I need a little bit more convincing on the alignment being something that's interesting.
Okay.
Right.
Mm-hmm.
But the debate is there. 7.6 sigma deficit of transients in the umbra. That's not something that I think we can ignore. I think it forces a shift from, are any of these transients real, to, okay, given a significant fraction of them are probably real sunlit objects, what are they? Mm-hmm. Okay. It's certainly giving me pause. I'll be honest.
Which I want to say for the audience, I've been working this guy for a long time. So to be giving him pause, is that's statistically significant.
Yeah. You probably have the number of times you've tried. Nah.
I've tried so hard, but I thought you'd find this interesting, even just from the experimental design perspective, the clever approach of trying to do a study like this in a way that's compelling.
Yeah, clearly, the team. The team in the PASP paper, at least, the one in the Proceedings of the Pacific Astronomical Society, That one has done its job of like, going through the proper science and things like that. The time stuff I'm a little less excited about, but the one with the Earth shadow thing, that's just like solid calculation,
Good math.
Yeah, that's just like good math. There was one that was kind of interesting. So candidate 5, the 5 transients systematically in alignment, that happened on July 22nd, 1952. They mentioned
27th.
Oh, yeah, July 27th, 1952. And they mentioned that this coincides with the most intense weekend of 1952 Washington, D.C. UFO flap, which I hadn't heard about, but I looked it up. And we've got a photo showing like the recorded number of incidents that were reported. And apparently like there were visual sightings, fighter jets were scrambled. There was a press conference from the Pentagon. So I didn't even know that this thing happened.
So this is one of the things.
That's weird, bro.
So this is one of the things that's so interesting.
Why would they do that?
It's so interesting because this is why when I start at the beginning of this, there's this whole legacy of this subject that exists that's very dense and there's a lot of information there. And unless you have an entry point, you won't know it's there, but UFO flaps are consistent and persistent throughout the history, not only of the US but global society, and it is interesting to see how it cyclically comes back up. But that was candidate 5.
Yeah. And that was the one that was like super aligned. I mean, I still think it's probably coincidence, but it's an interesting coincidence, I'll say that. The other thing they do at the end of the PASP paper is they look at 3D simulations in Blender and show how these reflective objects, if they're like slowly processing something that has a shape like that, could create the kind of signature that we see where like randomly it's at exactly the right angle where it's reflecting the sun into the Palomar telescope and then it goes away real quick. So then you get a really sharp, image speck in your photographic plate. It's speculative at best. I think it's certainly interesting. I think the Earth's shadow thing is the one that like is really like sticking with me. Right? That calculation is quite nice. And the way that they do the way that they do the controls where they simulate a random subset in that photographic plate and say, okay, how many are going to be in Earth shadow versus not? Like, yeah, that's seems to be the way that I used to do, like, these bootstrap things to try to figure out what the significance of my result was. So yeah, I thought it was pretty cool. I think next steps would be to just look at the photographic plate, make sure that it's not a defect.
Take a look at the plate, not a defect, and then from there, if proven to be the case, now we can have the next stage of the conversation.
Yeah, which is like, okay, and like, with modern surveys, perhaps there's a way to get an idea of how often this is happening in Vera Rubin. Vera Rubin's completely public, right? All of the data is public, like immediately after it's taken.
And it's up and running right now.
Yeah. So we have already 3 months of data from the Vera Rubin.
If you've not already listened, take a look back to our previous episode where we covered the Vera Rubin Observatory, why it matters. It's another sky survey, but it is just light years in terms of the structure and substance of how it works and what we talked about, the data, the immediate data availability.
Yeah.
No embargo,
Yeah.
Again, some people be like, well, the government's gonna like try to like wipe away their classified projects that are
but this is just, and it's been, I think, let's say 3 months.
Yeah.
3 months, meaning 100 days, meaning there's 30 photos of the entire night sky already.
Right.
Palomar took years for one photo of the entire night sky. This already has 30.
It's an incredible, the largest camera.
Yeah. The largest camera in the world.
Creating the biggest amount of data.
Yeah.
And one of the most incredible data processing and distribution platforms.
Yeah. It's insane.
It's just an incredible. So the point here being, there are things that can be drawn from this study in terms of now looking at us having this larger, much more robust data set and applying some of those thoughts and learnings to it, in addition to continuing to validate and replicate using the plates from the Palomar Sky Survey as well. Like there's multiple avenues of exploration here around this idea of these transient light artifacts that are occurring. I really was excited to just get your perspective on this.
Yeah, I thought it was a cool set of papers. Yeah,
and
definitely the PASP one I liked,
and just also talking about it from first principles. Again,
yeah, I think it's important to understand because this is historical data. We're not used to analyzing that, right? And the analog nature of it. It's not digital, right? You're not sticking a CCD in the back of a telescope. This is, at the end of the day, a chemical reaction that's giving us something. So it's important to understand the whole chain of custody,
right,
from photon to pixel,
right, and how do we even get to pixel from photon? An incredible set of stories this week. We did our lucky number 3. We started with our generative AI for cancer detection out of University of Toronto. Again, sorry again about the loss, but you're going to save the lives. You're going to save the lives of millions of people.
Yeah, that was great.
With that great story, followed up by our super story on the wireless retinal chip. We're making blind people see again.
Yeah,
not
wireless,
restoring.
Yeah, restoring,
not stopping, not slowing down, restoring.
Yeah,
and we ended with our interesting possibility of data related to what have now been renamed UAP, formerly known as UFOs, and these transient, pre-Sputnik transients in the Palomar Sky Survey. I'm very interested to see people apply some kind of similar methodology to the Vera Rubin data sets. They're there. They're publicly available. If you're interested in working on that, please shoot us a DM. We can make the connections. Episode 15, we're continuing to cook. Unbelievable engagement on just, I still can't believe people care about science as much as they do.
Yeah, I love to see it.
You do love to see it. Science is important. We are not covering, I know people are begging us to cover 3i Atlas.
Yeah.
There's no data. The government shut down.
Yeah.
There's no data for us to cover. However, Europa Clipper is in the tail.
Yeah.
Right now.
As we speak.
Right now.
Yeah.
But we can't do anything.
Yeah.
Because there's nothing to talk about.
The ESA and the guys around Mars have taken photographs of 3i Atlas as it went across. It's gone through the closest point of approach from the sun, and now it's on the other side of the sun, so we can actually see it again from the Earth. It's on its way to Jupiter. But we have no data that we can talk about.
So until we get the data, we won't cover it.
Yeah.
I know that Avi Loeb has talked about the non-gravitational acceleration, which can have a prosaic explanation, but we can't know whether it is that prosaic cometary tail or thingy or not until we get the data.
Yeah.
So we hear you guys. You want us to cover 3i Atlas. Open up the government, give us the data, and we will talk about it.
Yeah.
I am your host, Nare, joined as always by my co-host and our resident PhD, Krishna Choudhary. This is From First Principles. We'll see y'all next week.